In this goal, we are going to learn about the common ion effect and buffers. We already know about the common ion effect. It is essentially Le Chatelier's principle. And as we are not using gases in any of these aqueous equilibrium systems with acids and bases, we are just concentrating on add away, take towards. So if you add something to the reactant side, that will push the equilibrium towards the product side, so there'll be more products than reactants. And if we add something to the product side, that will push it towards the reactant side. And so there'll be more reactants. We also can remove things, so remove species. So if I remove a product, that will drive the reaction towards more products. And if I remove a reactant, that will drive the reaction towards more reactants. So that's the take towards. So remember, add away, take towards. So we have three different things that we're going to add to our system here. The first one is Kf. So we need to look and see if there's a common ion. So I'm going to look and see how this dissociates. So Kf is going to go into K plus and an F minus. So this means my F minus is a common ion, so if I add that to this weak acid solution of hydrofluoric acid, I'm adding a product that's going to drive the reaction towards the reactants. So I will lower the H plus and I will raise the HF. So I'll end up with more reactants. Let's do the next one. So on this next one, we have HCN. So it is weak, so I'm going to have a double arrow. The salt above just had one arrow. All right, so I have Cn minus, that doesn't match up, but I have an H plus that does match up. So when I add HCN, that is going to increase or add this H plus. This will cause a decrease in the F minus and again an increase in the HF. So if I add again to the product side, it's going to go this way, and I'm going to end up with more reactants for this one. Let's do the next one. So this is NaCl. So this is a salt, and so it's going to dissolve. It also has an alkali metal ion, just like the potassium that's just two above. The sodium ion, it will all dissolve. So I'm going to look and see what the common effect, or excuse me, what the common ion is. And I have an Na plus and a Cl minus, and none of those match, so there's going to be no effect. There is no common ion. So what is this going to happen, or how is this going to affect the pH? Well, in that first system, my H plus went down. Because it went down, then that means my pH went up. So this became more basic or less acidic. So what I would expect, again, the pH to go up. In that second one, the same thing. My hydrogen went down, so therefore the pH went up. And again, it would be more basic, it would be less acidic. And then on the sodium chloride, what would happen to the pH? The hydrogen ion would stay the same. And so because of that, whatever your starting pH would be the ending pH. So you would end up with the same pH, whatever it was when I started. Let's look at polyprotic acids and the common ion effect. Remember, polyprotic acids just means it has more than one hydrogen. So in carbonic acid, it's H2CO3. So remember, with acids, they lose their hydrogen ions one at a time. So first I'm going to dissociate the first acid, the first hydrogen ion, and then I still have this species that has an additional hydrogen, and so it is going to give me a second one. Now, what is the effect of the second hydrogen produced? When it makes this, it's essentially adding hydrogen ion. So when you add to one side, it's going to push it the other way. So polyprotic acids, they have very, very low dissociation of that second hydrogen ion because it inhibits itself. So as soon as it dissociates that second hydrogen ion, it's going to, through Le Chatelier's principle, drive the reaction towards those reactant sides. Now let's talk about buffers. In buffers, we'll see these common ions and the common ion effect. A buffer solution is one that resists the change in pH when you add a base or when you add an acid. And in the human body, there are many proteins that are pH specific. A buffer preserves the pH by absorbing or releasing hydrogen. A good example of how sensitive the body is to pH levels would be your blood pH. So normal blood pH is around 7.4. If you get down to around 6, 6.5, that is sure death. If you get up to around 8, you would also die. And so how the body regulates the blood pH is through our intake of carbon dioxide. So if you were to, for example, hold your breath, if you were to hold your breath, that would cause your carbon dioxide levels that are in your blood, they wouldn't be released. And so that would be essentially adding CO2 to this equation. So what's going to happen is it's going to drive the reaction towards the left. And over towards the left, this is where we have our hydrogen ion right there. And this is what determines the pH. So if you were to hold your breath, you would essentially be acidifying your blood. And what would happen is you would go into acidosis and you would pass out. And because you're passing out, then you would stop holding your breath. So imagine a toddler throwing a tantrum, holding their breath. This can happen. So as soon as the little toddler passes out because of the acidosis that they're causing in their body, then their body will start breathing normally again and this system can work again. So the CO2 in this case then would be removed by the breathing normally, and that would drive the reaction this way towards a normal pH in the case of the toddler holding their breath. The same thing can happen to somebody that's hyperventilating. So let's say that you are really stressed out and so you're hyperventilating, and what's happening is you are removing that CO2 and you will pass out also. And it's because this time your blood goes into alkalosis. And after you pass out, you'll start breathing normally again. And this will add CO2 now to your bloodstream because you're breathing normally again. And that will sway the pH back to normal. So in this way, the breathing regulates what the pH of your blood is, and it keeps it just right pH. So if you were to say drink some lemonade, if that would somehow affect your blood pH through this buffer system with this carbonic acid, you would be able to regulate your pH and keep your blood exactly where it should be at 7.4. A composition of a buffer. What is a buffer? A buffer is a weak acid and its salt. Essentially, it's a mixture of its conjugate base and the weak acid. And they have to match up. So make sure you're really careful to match it up. So for example, HF, this would be my weak acid. And then if I had NaF, because this dissociates into that fluoride ion, this is your common ion. It is also your conjugate base. So this is the conjugate base. If I were to add this to the weak acid, then I would get a buffer solution. So essentially, I would have extra of this fluoride ion, but it would be in this equilibrium system driven more towards the HF because I just added some extra fluoride ion. A buffer can also be a weak base and its salt. So that would be its conjugate acid. So a good example of this would be ammonia and ammonium chloride. Now remember, with bases, you need to add them to water because they need to gain a hydrogen ion. So when I take the salt, so the ammonium chloride, you can see that there is a common ion, that ammonium ion. So when I add this to my weak base solution, it's essentially adding extra of this. So that will drive the reaction this way. So I'm going to end up with more product side. But this is a buffer situation. So notice that when you're adding a salt, you're always going to add the salt from a strong acid or strong base. So for example, in the first one, Na, that comes from NaOH. So I know that's not going to participate in the reaction, it will dissolve. And notice that in the Cl minus, so this comes from your strong acid. So again, it's not going to participate or influence the pH in any way. So they're going to be neutral. The best buffers have a significant quantity of this conjugate acid or conjugate base. So what I put for extra in each of these examples. And if there's equal amounts of the acid and the salt, or the weak base and its salt, that's even better. Now, how do buffers work? So here's just a general buffer right here. Again, this is going to be a weak acid. And again, with its conjugate base. And you can see its conjugate base right there. Okay, so weak acid, its conjugate base, and this is a buffered solution. So what would happen if I were to just take a strong base? If I were to take a strong base, then the following reaction would occur. So here's my strong base, the OH. I add it to the weak acid. And anytime you add a strong anything, a strong acid or a strong base to a solution, it will always drive the solution to completion. So by adding my OH, it's going to cause this weak acid to completely fall apart. And its little hydrogen ion is going to react with the OH and make that water. And it will keep doing this until you run out of OHs, or until you run out of the weak acid. But now normally adding OH would increase the pH, but as long as you add just a little bit of the OH minus, your pH is going to be balanced. And that's because the weak acid will fall apart a little bit to absorb those OH ions. So the OH ions, the hydroxide ions, aren't allowed to accumulate, and because of that, they don't affect the pH. They might affect it just a little bit, but it's going to keep around the same pH as you started. Now, if you added a strong acid, so in my last example down here, if you add a hydrogen ion, then this time the conjugate base is going to absorb it. So the conjugate base will absorb it and drive it the other direction. So again, you don't have hydrogen ions hanging out there being allowed to accumulate. And so this keeps the pH approximately the same. So you can see your example right here in the picture. So in this picture, we have our buffer system. If I add a base, you can see how the acid absorbs it, so it goes down just a little bit. And if I add the hydrogen ion, you can see how the conjugate base will absorb it. In either case, adding a little bit of acid or a little bit of base, the pH should change just minimally, so not very much. And again, that's because either the weak acid will fall apart to absorb the OH minus, or your conjugate base will absorb the hydrogen ions to form that weak acid.